Thank you for viewing this recorded Reliable Automatic Sprinkler Company webinar. Should you have any questions regarding this presentation, please feel free to contact Reliable Technical Services at 800-557-2726 or email us at techserve@reliablesprinkler.com. For upcoming webcasts and an archive of past webcasts, please visit reliablesprinkler.com/webcasts. Once again, thank you and enjoy the presentation.
Again, my name's Phil Friday. I'm with the Reliable Automatic Sprinkler Company in our product services department. And here today to talk about some large-scale testing we did last year related to several of our products, but primarily our TNL 280 tunnel nozzle. So let me begin. And I just want to check real quick. Let me stop this for a second and then want to make sure we have sound. I apologize for the interruption there. Got to have the sound on the videos. Okay. So hopefully everyone can see my screen again and we're sharing sound and we're ready to go. This is related to, presentation is really related to a product journey. And I want to start by talking a little bit about that particular product and its journey, and then how it led us to conduct a series of full-scale tests last year. And we're going to share the results and share that experience with you. So I hope you enjoy. Tunnel application. So in the late 2010s, we developed a spray nozzle specifically for tunnel applications. And we designed it, developed it, and went and got it listed as a spray nozzle with UL. But it's interesting, with spray nozzles, you don't necessarily have to conduct large-scale testing. What you do is you outline the design intent and parameters for the nozzle, and then they test that the nozzle meets those functions or meets those specifications. In particular, it is, of course, it's rated at 175 psi or 12 bar. I'm going to try to make sure I talk in both metric and imperial units for everybody. It's a K400 nozzle, so it's a large nozzle. We'll talk a little bit more about that. If you're in the US and some other places, that would be a K28. And it's really designed to provide an extended coverage spacing, 5.5 meters by 5.5 meters or 18 by 18. It's got a very unique corrosion-resistant coating. This was a new development for us, the Rasco 500 ceramic coating. Most nozzles that you see that are corrosion resistant are either some corrosion resistant material like stainless steel. It's very expensive, or they'll use an ENT or coating. And we developed this coating because it's very durable, and it's also non-reflective, which is important in a tunnel environment. Uses our W5 wrench, and if you want to get more information specifically on the TNL 280 nozzle, go to our website and you'll see, you'll be able to navigate to Technical Bulletin 099 and get all the technical details, as well as some other information on the testing and so forth. Get asked a lot of times about the spray pattern. That's a typical input that's needed for design functions and design purposes. And so here's what that the spray patterns graphs look like, metric on your right and imperial on the left. And so these are at two different pressures. One is at 0.5 bar, which is the red line. You can see the colors. And the other is at 20 psi or 1.4 bar. Interesting question that comes up a lot of times when folks look at a spray pattern graph like this is, why is it narrower at a higher pressure? And that's a typical function or feature of some of these larger nozzles, where the spray pattern will contract when you start to operate at a higher pressure. So um, after we got the listing, we were involved in a number of tunnel projects. It's been used around the world. But some of what we learned during, as we were involved in those projects, is there's a desire for there to be some large scale testing in support of a fire protection system for tunnels. 2024, we looked at our research budget and said, well, let's go do this. And the first thing we had to do was go find a test facility. And so we found a facility that's dedicated to this specific kind of testing. They do not only large scale testing for manufacturers evaluating systems or items, but they also do firefighter training for tunnel applications. So we found a facility, this A-plus facility in Asturias, Spain. They had a 600-meter long tunnel. It's about 9.5 meters wide or 30 feet wide, 31 feet wide. Has a height of about 5.2 meters. In the test area, which there's a false ceiling in the center part of the tunnel where a lot of the testing gets conducted. They put in a fireproof false ceiling. And we installed a deluge system that had our TNL 280 nozzles connected to it. Talk just a little bit more about the facility. This is an overview in a drawing format, maybe a little easier to envision with a satellite view. If you have an opportunity to go to this facility, I strongly recommend it for testing or for firefighter training. But here it highlighted in yellow, you can see the 300-meter long tunnel and that test facility in Asturias, Spain, which is on the northern coast of Spain near the ocean. And this is a quick, fun video that we put together that shows kind of a drive around of the facility, a couple of snippets from the fire testing. So I'll go ahead and play this real quick. We had fun putting that video together using only cell phones, or mobile phones. So I hope you enjoyed it. Give you a little bit of a layout in terms of the instrumentation to try to get you oriented as we start to get into talking about test details. And so this in the top is a plan view of that center section of the tunnel. Just point out a couple of things. Measurements are taken both upstream, and if you can see the numbers, you'll see U10. This is 10 meters upstream of the center line of your main commodity. And then measurements downstream. So here is 10 meters downstream of the center line of the main commodity. This is the main array of a pallet configuration. And so we'll talk a little bit more about that as we move forward. And then this here is a target stack of pallets. And then maybe one of the more important locations that we're going to refer to, there is a thermocouple placed downstream of the main array that was used for measuring or determining the activation time based on the temperature of that thermocouple. So you can see it's in the bottom elevation view. It's about 0.3 meters below the ceiling, and it's centered along the same location as your target array. Here's an image that'll give you a 3D view of what it looks like with fire burning in the tunnel. This is the test section I referred to. You can see that fireproof ceiling above. Here you see 3 lines, or 3, we'll call those branch lines, that nozzles are connected to. And in our testing, we're going to talk about 2 different configurations that we're testing. One is where the center branch line was active, and the other two were not connected to the water supply. And the remaining tests were only the outer two lines were connected to the water supply. So we were wanting to look at tunnel configurations where you may have a narrower tunnel and you're able to, because of the spacing, you only need one line down the center, and other configurations where the tunnel may be wider and you would need multiple branch lines. So we wanted to look at test configurations that addressed both of those situations. Performance criteria. So there's really three main performance criteria that were looked at during the test, as well as what the heat release rate, were temperatures. So temperatures both upstream and downstream, at that 10-meter downstream of the center line of the main array. One of the goals was to not exceed 60 degrees Celsius within 120 seconds of after you activate your fixed fire suppression system. And so you can reach 60 degrees Celsius before the system activates. It's really looking at how do you perform after the system activates. The heat flux is another criterion, and heat flux was measured about 6 feet up and both 15 meters up and 15 meters downstream. So that's 1.8 meters high. I think that's about head height. And you're trying to, the goal is to not exceed 5 kilowatts per square meter heat flux. And again, you're trying to do that no later than 120 seconds after the system activates. And then the last goal is you don't ignite the target array. And that's specifically for the pallet tests. And this is a summary of the tests, and I'll just walk through these very quickly. Test 1 through 3 were 150 megawatt pallet tests. And we tested two piping configurations, one where only one line was active, and the other two where we were testing between two. Here, when we're doing large-scale testing, we'll often refer to that as under one versus between two or between four. But this is referring to between lines. And then detection temperature. So typically in a test protocol like this, you would set your detection temperature at 68 degrees C. We wanted to kind of push the boundaries a little bit. And so our first two tests, we had our detection temperature up at 100 degrees C, which is 212 degrees Fahrenheit. And then after you reach the detection temperature, there's a time delay that is typically used. And that time delay is often 3 minutes. You can see there in test 2, we, again, trying to push the limits a little bit, we've had a 3-minute time delay. And then you've got a small water delivery time here that associated with how long it takes from the time you activate the system until water reaches the nozzles. And so if you add these the second and third, or these last two columns to get the total for the very last column, to get your water delivery after detection time. So So the first three tests, again, those were 150 megawatt pallet tests. So what does that mean, 150 megawatts? That is the potential energy release from if the entire main array of pallets burned, right? So that's the potential peak heat release rate. And that's associated with as you know, that many pallets. Test 4 was a diesel pool fire test. We're going to talk a little bit more about that, but that's one of our tests, or the test where things did not go as planned. We had an issue with the on-site water supply. It took about 7 minutes after detection for water to reach the nozzles. We think we had an issue with the on-site pump potentially cavitating, and those test results weren't necessarily useful for evaluating system performance, but I think they're interesting to share and talk about. And then last but not least, the EV test. And so we ran a test. We acquired 3 Tesla Model 3s, charged them to 100% stated charge, and um, and then put a fire underneath one of the battery packs to evaluate how the system performs. So let's dive into the details of our testing. There we go. So you've seen this image already, but this is these are the Class A commodities, your pallets stacked as well. So here's your main array on the left, your target array here, um, 5 meters downstream, and then we have an end view of the tunnel. This depicts a metal plate that's there to prevent. Intended to represent a shielded fire scenario where water isn't able to directly reach from upstream into the pallet array during testing. The Class B commodity, same tunnel, different commodity. You have diesel fuel and pans here. And let's talk through what happened during each of the tests. So in every test that we performed, we installed the nozzles at maximum spacing, and we operated them at minimum pressure. So this is the most you would space them apart and the very least pressure you would try to drive. And again, the reason there is to try to be very conservative in evaluating the performance. So test one, here are all the parameters. Again, it's a K28 or K400 nozzle, 5.5 meter spacing, half a bar nozzle end head pressure, and an activation temperature of 100 degrees C, which is one of our conservative measures, and the tunnel air velocity at about 3 meters per second. 3 meters per second is typical in tunnels, as well as in the large-scale testing conducted with tunnels. That represents about 11 kilometers an hour. And so we're going to talk a lot about the tunnel air velocity as we continue to talk about the testing. So here was the heat release rate. You can see it was capped at right about 14 megawatts. That's considered a successful test. You see the air velocity graph here where it's about averages 3 meters per second throughout the test duration. And then our heat fluxes. And so again, if you remember, the goal is to stay below 5 kilowatts per meter squared. And here you can see that the heat fluxes stayed very well below 5 kilowatts per meter squared. Here's a picture from that test just before the system was activated. Here's another picture from that test after the system is activated. Just want to point out again that you see 3 pipes, the 3 rows of nozzles above the test array. And in this under one test, in test 1, they only have nozzles active in that center line. Those perimeter lines were there. They're set up and staged for later tests. Here you can see shortly after system activation, the fire and the nozzles operating, and you can kind of see down at the end, that's what the end of the tunnel looks like. So you see what your smoke layer kind of looks like as well. System did a really good job under one, which is typical in large scale fire testing. Is usually, not always, but usually your under one test is the one you might wager on if you were wagering on pass or fail. Some of the post-fire damage that you can see from the pallets. And I would direct your eyes over to the right-hand side of the page where you can see the target array. Remember, that's one of the performance criteria. And it almost looks like those pallets are charred, but that's a shadow. There's not a mark on them. So we did not ignite the target, and that's always a good day when you don't ignite your target during a large-scale test. Test two was one that generated quite a bit of discussion here. And elsewhere, we decided to get really aggressive with the testing program here, or the test parameters. We kept the nozzles at maximum spacing. This time, the center pipe was inactive or not connected. We kept our activation temperature at 100 degrees C. We bumped the time delay from 2 minutes to 3. So we increased the time delay, and we wanted to do an air velocity that we haven't seen published as part of a large-scale test program in a tunnel. And so we haven't seen anything above 3 meters per second. So we ran it. The goal was to run it at 4. Turned out it was averaged 4.7 meters per second during the test, which that's about 17 kilometers an hour of airflow. And it had a significant impact on the results of the test. We still were able to achieve fire control. Remember, this is a potentially 150 megawatt fire. Here we limited the heat release rate to 65 megawatts. Still a big fire. Here's your air velocities, and you can see for a significant portion of the test, they're kind of after minute 15 and going on through minute 20, you can see that the air velocity was higher than 5 meters per second. A lot of airflow. Here's your heat fluxes. Remember our target. I should have a line across here, but if you can envision it, at 5 kilowatts per square meter is the criterion we were looking at, or that is your performance criterion. And we're able to maintain the heat fluxes well below that 5 kilowatts per meter squared. Here's an image from the test. Just after system activation, you can maybe make out some of the water droplets. And we won't watch a video of this. We'll get to some videos here in a little bit. And again, in the remaining tests I'm going to talk about during the presentation, the webinar here, only these perimeter lines, one that you can see on this image here, and then one you can't see that's outside of the view. Those are the only ones that are active. Post-fire damage assessment, and so you can see that some of these pallets are consumed, but there are quite a few left. And then here's our target. And while we have some charring of the target that probably happened before the system was turned on, we did not ignite the target downstream. So it was a good result. We wanted to do it again to see what it would look like if we ran more of a standard test protocol. And so that's what led us into the parameters related to test 3. Same nozzle spacing, nozzle pressure at minimum 0.5 bar or 7 psi. We lowered the activation temperature down to what's more of a standard for tunnel safety testing, and that's 68 degrees C or about 155 degrees Fahrenheit. Backed the time delay down to 2 minutes, and then kept the air velocity about 3 meters per second. And so this is an interesting comparison. Here we were able to keep the peak heat release rate well below 40 megawatts, achieving fire control. And here's a graph showing the average air velocity in meters per second. You notice this is not an exact science. It's an exact science. It may be more difficult to measure and keep at exactly a certain airflow. One of the reasons you see fluctuations in this graph is these graphs is because of the wind. And so, wind entering the tunnel and exiting it can have an influence on how much air velocity you're moving through. So it's something that does fluctuate slightly. Heat fluxes, here the top of the chart is shown at 5 kilowatts per meter squared. And we were able to the system was able to limit the heat fluxes to less than 2.5 kilowatts per meter squared at the peak. Here's an image from test 3. And you've seen this image before, but this really clearly shows uh, the piping configuration, and your center piping is inactive again during these the remaining tests we're going to talk about. Um, the Another image from test 3, just after the system was activated. And yet another one. It's always good to see fire testing images. We're going to watch some videos here in a minute. And here's some of the post-fire pallet damage. See quite a bit less consumed in the test 3 than test 2. Another image of our post-test pallet damage in test 3. If you look off in the background to the left, you'll see the targets were untouched. And I'll say again, it's always a good day when you don't ignite a target in a large-scale test. Test 4, this one is interesting. It's the one I mentioned that we ended up having to consider a no test after evaluating all of the test data. So this was a 60 megawatt pool fire test, diesel pool. So it's a fire that grows very large, very quickly. Same nozzle spacing, same nozzle end head pressure, 0.5 bar, 7 psi. The activation temperature was at 68 degrees C, 155, and a 2-minute time delay with an air velocity of 3 meters per second. When there's something about a large scale test that calls the data into question, we can that's referred to as a no test. And so here you can see the heat release rate chart next to the system pressure, nozzle pressure graph. And I would just point out that it was this ramp up that started at about 4.5 minutes, and it took more than 3 minutes to get up to this point, and then finally got to system pressure. But by that time in the fire, if you take your eyes back over to the heat release rate curve, we're already in the decay phase. It's hard to say what impact you had on that heat release rate curve. Some we believe, but the results are still interesting. Average air velocities. So this one was set up so it would be a 3 meter per second. I think maybe because of some of the environmental conditions, you see some of that fluctuation, but it did average out at about 3 meters per second air velocity. Heat fluxes are way up there, and so as would be expected of a fire like this, and with the system not operating until very late. And now let's talk about maybe what many of you came here to learn about, which is the electric vehicle testing we did. So as part of this, and it's something that we like to do if we can, is if there's an application that we have designed fire protection equipment for, we like to see how it performs in a real world application. So much like our LB11 nozzle that was developed a few years ago, we went through the large scale testing associated with the listing requirements, and then on our own we went out and did some battery testing. And so we wanted to do the same thing here with the TNL 280 nozzle, where we wanted to look at how the system performed with real vehicles in a tunnel, and for those vehicles we chose to use electric vehicles. And specifically, we acquired 3 Tesla Model 3s at 100% state of charge, and we charged them to 100% state of charge. We also got a internal combustion engine vehicle and positioned it downstream. And the goal was to simulate an event involving multiple vehicles on fire and how the system would deal with that. Um, so here is the test layout, and um, you can see, so each of the cars is spaced 1 meter apart, side to side, front to back. And this was the layout. And so here are where the EVs were, and here it shows where the internal combustion engine vehicle was. Again, the airflow in these tests moves from south to north. So left on your screen to right on your screen. If you're looking at either the side view or the top view. And so let's spend a minute before we get into some of the videos looking at the heat release rate curve. And so I do want to mention at this point that the air velocity during this test was 2 meters per second. And you may immediately ask, well, why didn't you do it at 3? We did it at 2 meters a second after doing some evaluation of the ignition package for the electric vehicle, where we custom built, or the lab custom built a pan burner that was designed to be about an inch from the bottom tray of the of one of the electric vehicles, to try to get the maximum amount of heat on that bottom tray, through the bottom tray into the battery pack that we could. The goal was to try to get into thermal runaway, and a fire that was the result of thermal runaway in a vehicle, as opposed to just a typical vehicle fire. So you can see on this heat release rate chart, we have fire detection, and it took almost 45 minutes in order to get the vehicle. So let me back up. It took just less than 45 minutes to get the vehicle started into thermal runaway. So this first spike is when you start to see thermal runaway in the first vehicle. Fire detection didn't occur until several minutes later. And then system activation, we implemented a 3-minute delay in this test to try to keep things challenging and make sure we had a well-involved vehicle fire or multiple vehicles on fire before we activated the system. So you can see that by the time the system was activated, we had almost gotten to the peak heat release rate that the fire would get to. Here's that 2 meters per second air velocity. I kind of got ahead of myself and talked about that already. But again, we ran it at 2 meters per second for that particular test. We didn't, I don't think I got to the point about saying we didn't want to have airflow significantly impact the igniter for the electric vehicle. We wanted as much heat as we could being applied to that battery pack, and we felt like a higher airflow would have had a negative impact in that regard. It would have taken us longer to get the battery going. Here's your heat flux measurements, and again, if you remember, 5 kilowatts per meter squared is the target. You're trying to get make sure you reach that target within 120 seconds after you activate the system. And so after we activate the system, those heat fluxes drop very quickly. So let's watch a video of the electric vehicle test, and then we'll talk about it a little bit afterwards. So that video, and I'm going to play it one more time, was taken right after thermal runaway started in that first vehicle. So let's look at it one more time. So it's long before the system is activated or detection occurs, and you can start to see where the adjacent vehicle is starting to be exposed to both flame and heat. Let's watch another video or another view of it a little bit later into the test, and then we'll talk about this one as well. Okay, so that showed various stages in the fire. Um, sorry, and so here's some thermal imagery from those various stages. Um, Jakub Bialowski from ITB, I believe he works for Wojciech Baczynski, was there at the test with us, and he took some thermal images as the test progressed. So these are interesting to look at. I do want to point out that each row, these 3 rows of images are all the same. They're just in different color shading. So pick your favorite shade of blue or red or green, and then follow along from left to right. So on the far left is 5 minutes before the beginning of thermal runaway. So that's probably about 38 minutes, 39 minutes into the test. Thermal runaway in the second column. You can see what that looks like. Some of the heat starting to expose the adjacent vehicle, and we don't have images of it, but certainly the downstream vehicle as well. Just before system activation, again, you can see that adjacent vehicle is well exposed to heat. And in fact, that second vehicle, that adjacent vehicle, was ignited before the system activated. So we had two, maybe 3 cars involved by the time we turned the system on. 5 minutes after system activation, there in the 4th column, the 4th image from left to right, and then 10 minutes after system activation. Really a good way to look at and represent how, a timeline of a fire test. I thought that was a neat way to do it. So another interesting exercise that we performed while we were there at the test facility is we wanted to look at the influence that air velocity in the tunnel has on the discharge pattern of the nozzle. And so I want to walk you through that, and we can have a little bit of discussion around it. But what we did is we actually shipped some of our lab collection buckets from here in South Carolina over to Spain, and we set them at the ends of the system. So we set buckets up on the upstream or upwind end to capture half of the discharge of a single nozzle. And then we set a group of collection buckets up downwind at the very end of the system that was set up. And so just something to point out here is that the collections that I'm going to share with you do not include nozzle overlap. And so, if we were wanting to look at nozzle overlap, we would have placed those in between nozzles. And so just here's the image of the locations before we get into what the results were. So you've got your blue dot, which is representing a nozzle overhead, and your black squares are the collection buckets that are set up both downstream of your downwind nozzle and upstream of your upwind nozzle on the ends of the system. So no forced ventilation now. It actually wasn't, but there was ventilation because of wind or the environmental conditions. So they were measuring about 1.4 meters per second of natural ventilation in the tunnel when these control measurements were taken. But you can see, and this is just the downstream collections, fairly even distribution. I do think that air velocity had some impact. And then what happens when you have a forced ventilation of 3 meters per second? Well, this is interesting. Not necessarily what you would think. In your downwind collection group, which is the top, you would think it would improve collections towards the end. Um, Certainly, you would expect it to not improve the upwind collections, but you see something that you probably don't expect, which is these collections immediately downstream of a nozzle at 3 meters per second aren't what you would expect them to be. Now, if there were two nozzles there, you'd probably be in good shape. Um, but it's an important parameter to evaluate. And you'll see as we get into even higher ventilation rates, here's an image real quick of what that nozzle spray pattern looks like at 3 meters per second air velocity. And you can definitely see a tilt to it. There's a lean there. Now you crank up the air velocity really high, 4.5 meters per second is a lot. And you see that what the distributions look like downstream and upstream. Now, upstream collections, so those are these on the bottom, that kind of looks like what you would expect. But these downstream collections are very different from what we saw with 3 meters per second. And so keep in mind, these collections are with a fairly large nozzle that that delivers fairly large water droplets, and as designed in order to achieve optimal cooling. And those water droplets of any nozzle I can think of are going to be the least susceptible to influence by horizontal ventilation, and yet they are influenced by it. And so it's important to keep in mind, regardless of what your suppression agent is or how you're delivering. So whether you're using water from a sprinkler or water from a nozzle or low pressure water mist or high pressure water mist, it's important to evaluate in a large scale setting what the influence is of that ventilation on your extinguishing agent. One last video before we get into some of the system design features. I do want to say very briefly that although this car was burning before the system was activated, the system was able to prevent the battery from ever going into thermal runaway. So that was a good thing. We think that was a tire exploding, although many people might assume it was part of the battery. It's always an exciting video to watch. Let's talk about some of the system design features and recommendations that, and this is the things that we've learned through both experience testing. So valve recommendations. For a system like this, you would use a deluge valve. There are 4 options that Reliable offers. We have our DDX deluge valve, if you just want a typical deluge valve, and then we have our newer diaphragm deluge valves, which are the DDV valves in 3 different configurations. And a couple of those features of those valves that are important for a tunnel environment is, one, is because of the length and elevation changes associated with many tunnels, most tunnels, is you will want some kind of pressure reducing function. And our DDV with remote resetting pressure reducing option offers that pressure reducing function that kind of gives you a two-in-one. And then many tunnel applications, you need to be able to turn it on and off remotely. And so we call that remote resetting. And so if a tunnel has a command center where they want to activate the tunnel from a remote location, you would want a remote resetting function where you can both energize and de-energize the solenoid specific times. 4 to 6 inch valves are the typical sizes we see used in an application like this in tunnels, although it really depends on the hydraulics and the system design. Different solenoid options. So we offer both a latching style solenoid for systems that require FM approval and a non-latching style solenoid for systems that don't need the FM approval. And so you can get options in 300 psi rated to 175 psi rated. It just depends on what you need and trying to do. Recommended piping and hydraulics. Let's talk about this from some of the things that we've seen. So in general, you have 6 nozzles on a line, you can cover about 33 meters of tunnel distance. And so that distance works well hydraulically and keeps your pipe sizes lower. And ultimately, though, this has to be determined by the engineer of record. But a system set up like this with these nozzles would be flowing about 75 gallons a minute per nozzle if you're at 0.5 bar. So pressure reducing valve outlet settings, generally 50 psi outlet setting pressure at the discharge of the pressure reducing valve is sufficient. We offer pressure reducing valves if you choose not to integrate it with your deluge valve. We get a lot of questions about how the pressure reducing valves operate and settings and so forth. And so here it just depicts a pressure reducing valve in these tree type systems to help you manage pressures downstream to the nozzles. All depends on your hydraulic calculations and your water supply. But if you've been involved in any kind of tunnel work, you've dealt with this issue. Wanted to take a minute to thank some of the folks who helped us along the way during this test program. A+ Laboratories, Pathisa out of Madrid. I mentioned ITB. I got a little bit of consulting work out of Baltic Fire Laboratory, so we appreciate their help. And then, of course, the entire Reliable team here that worked hard to get this done. There was a lot of back and forth on airplanes, and it's a lot of coordination. Of a fun project, and so appreciate everybody's hard work. So with that, we've got about 7 minutes left, and I will leave the rest of the time for questions.
All right. So Phil, just 2 questions in the chat today. First one being as it relates specifically to the diesel pool fire, and I kind of someone asking you to speculate a little bit about. So if we were looking at water deluge in that environment or foam in that environment, how would one compare to the other?
I don't know because I haven't tested it.
Okay.
So it's a good question, and I don't want to speculate. I don't have a great answer for it. Foam does a good job with liquid fuels, typically, but I think some of the things that you've got to consider is containment, right? I mean, if you're going to put foam on the ground, you got to figure out a way to contain that, and then you got to look at your slopes within the tunnel and things of that nature. So, you know me, I hate to speculate. I'd rather go test it.
I think that makes perfect sense. And then just one last question. In the tunnel, we have someone who's working on an underground metro project that involves tunnels, and they're wondered if we thought this would be a good application for this type of product.
Oh, absolutely. Yeah, as long as this would be a great application for both road tunnels or rail tunnels. And so they, want to have a conversation more about it and try to get into some of the details, we can do that. But if it's a rail tunnel application, it's certainly right in the wheelhouse of the equipment we've talked about.
Okay, one last question that just came in, and I don't know that we could really speak to it, but let me throw it out there anyway. What kind of pipe did we use in this particular application? Was it galvanized? Was it not galvanized? And would we have a recommendation for what should be installed in that environment?
Yeah, that's a great question. We used black steel pipe in the testing. And so I think you need an evaluation of the environment and so forth. And um, I wouldn't, you know, galvanized probably wouldn't be a bad idea. Um, Black steel may be adequate. And so I would have to go look at some of the projects we've been involved in to see if there was something uh, beyond black steel that was selected.
Okay, great. And one last one that just came in. What type of detection do we use in this environment?
So there wasn't an actual listed detection used. It's typical of a large scale test where you just use a thermocouple to measure temperature. And so if I go back to that, if I went back to that slide, I'll show you where that detector was located. There we go. Can we see it? There we go. So here was a thermocouple, a Type K thermocouple that was positioned in the tunnel just below the ceiling, you can see, and downstream of the main array. So that's where it was located for all the tests, and that's what they used to determine when you reached an activation temperature. But you could use a standard heat detector for that. You could maybe use linear heat detection, all kinds of different options to evaluate there.
All right. Well, there's a couple more that came in late, but we will answer those individually going forward. Thanks, Phil, for an awesome presentation.